Okay, measuring segments. We understand that a segment is a defined section of the line with two endpoints, and our concern is how far apart are those endpoints? So how long is that segment? So our segment can appear in a few places. It can be on a number line, it could be on a coordinate plane, or it could be on neither, and it's just part of a figure or even a figure on its own. Well, we're going to start with number line and coordinate plane. So measuring segments, first thing to understand is the way, again, stressing the way we write things in geometry makes a big difference. So if we have a segment named AB, well, with the bar above it, we're just naming it. Without the bar above it, we're talking about how long it is. Uh, how how long it is, or its measurement. Measurement. So we're identifying that we're talking about the segment going from point A to point B, or from B to A, doesn't matter, but we're referring to how long it is as opposed to just naming it. Remember, segment AB and segment BA are the same thing. So AB and BA are the same thing. Okay. So the other thing we want to notice right here is our congruence symbol. So congruent, and segments are congruent if and only if they have equal measurements. So congruent effectively means identical. Congruent, think about it as identical. Identical, identical. Identical in every way. Now, segments can't be equal. Their measurements are equal. Triangles cannot be equal. However, the measurements of their sides and angles can be. Triangles can be congruent, meaning identical. They are exact copies. Segments can be congruent. So a picture, a figure can be congruent, which means all of its measurements, all of its numerical values are equal to each other. Okay? And that's a really important distinction in geometry. It feels interchangeable at first, but they are completely different things. Congruence versus equals. And this last line here is an important idea. Okay, again, if we're naming it, we say congruent. If we're talking about their measurement, we say equal. So let's talk about measuring, and this is specifically measuring on a number line. We can subtract the values and take the absolute value. So measurement, for our purposes, cannot be negative. Measurement cannot be negative. Negative indicates direction. So if I put my car in reverse and drive a mile, I drove a mile. Negative might indicate that I was going backwards, but the distance that I traveled is 1 mile. So when we talk about the measurement of a segment, it cannot be negative. That's why we're going to take the absolute value. So if I think of this as a number line, for example, we'll look at the first one. And I have one point at 5 and the other point at 32. Rather than counting, I'm just going to subtract them and take the absolute value. Okay. And we can see whether they're in a positive position or a negative position on that number line. It's going to work. So we'll just do, an example or 2 here. In number 1, HI, well, we have H is at 6 and I is at 8. We're going to subtract them. So 8 minus 6 absolute value is 2. If we did it the other way, 6 minus 8 absolute value is still 2. So we get the same answer. It does not matter which end we start with. The measurement is the same. Let's do another one. Let's look at something like number 4, GE. Well, G is at -2, and E is at -9. So I'm going to subtract. So -2 minus -9 absolute value. So that's -2 plus 9 in the absolute value, which is 7. And if we went up to our number line and counted from G to E, 1, 2, 3, 4, 5, 6, 7. So it is 7 units. The fact that it's going left doesn't really matter because we're not talking about direction, we're talking about measurement. Now, when we get to the coordinate plane, it gets a little bit more complicated, but it's really not bad. We're going to use something called the distance formula. On the coordinate plane, we have x's and y's, so we can't just count. Now, if it is a vertical or a horizontal line, we can count, or we can just use the subtraction method because it's the same as being on the x-axis or y-axis, which are number lines. But if it's on any sort of an angle, we have to use our distance formula. And if you look at the distance formula, it's not terrible. In fact, we're familiar with this. y2 minus y1 and x2 minus x1, those are really just the elements of slope. We're just using our knowledge about slope and applying it in a slightly different way. So we're going to do the same thing. We're going to identify the two endpoints. We're going to get their ordered pairs, and we're just going to plug it in and follow PEMDAS. So let's look at an example. Let's do number 17. So I want to make sure that I have my distance formula handy. x2 minus x1 squared plus y2 minus y1 squared. Call one of them 0.1, call the other 0.2. It does not matter as long as you substitute carefully and correctly. So I'm just going to make this a little bit bigger. I'm going to call S 0.1, so that's x1 and y1. And I'm going to call R 0.2, x2 and y2. Remember, it's the x and y of 0.1 and the x and y of 0.2. Since this segment is on an angle, I can't just count. From R to S, it's 2 over, and it's 1, 2, 3, 4, 5 up. So I can count those parts, the rise and the run, and that's all. y2 minus y1 is rise. x2 minus x1 is run. So I can count that if it's easy enough. And this will absolutely work. But I want to plug it into the formula just to walk through it. So let's see what we have here. We're under this big square root. x2 minus x1, that's 2 minus 4 squared. And then y2 minus y1, we have a -1 minus 4 parentheses squared. Well, let's work that out. -2 in parentheses. Remember, don't drop your parentheses. We have to follow PEMDAS. -2 squared is a 4. Negative 5 squared is 25. That's going to give us the square root of 29. And if we grab our calculator and type in the square root of 29, we're going to get 5.385164807. And, well, this is where we have to stop and follow directions. Our directions up here told us round to the nearest tenth. So we're going to look at our work, our tenths. We look one past it, and we're going to say our answer is approximately equal to 5.4. 5.4. So approximately, because we're rounding, an equal sign is going to be acceptable. But that's our distance formula being used. So if, again, on the graph, maybe we can count that rise and run. That's not a big deal. We would have counted a 2 and a 5. And when we square the 2, we get 4. And when we square the 5, we get 25. And we're going to end up with the same square root 29. But it's important that we know how to substitute carefully and clearly, because we're not, we're not always going to have that graph in front of us. And sometimes putting it on the graph, the points are so far apart, it's not worth it. So we have to be able to use that formula. So again, let's just do another example here. We're going to find the length of the segment. So I'm going to do number 21 here. And I can count, obviously, but just for the purposes of this exercise, I'm going to say -8 minus -1 absolute value. So that is a -7 absolute value, and my answer is 7. So I can say that this segment measures 7 units. In the next set of questions, we're given the endpoints of the segments, and we're asked to find the length, but also determine or tell whether they are congruent. So we're going to do number 23. And I'm just going to make this a little bit bigger so I have room to work. So let's work on RS. So instead of saying D, let me, I'll write the formula out for us. So distance equals, it's a big square root, x2 minus x1 squared, y2 minus y1 squared. Instead of having a D, I'm going to make it say RS because that's the segment I'm working on. So RS equals. Now again, we need a 0.1, 0.2. Since they're just laid out there, I'm going to call this x1, y1, and x2, y2. So I'm just going to use them in the order that they were given. I have a square root, x2 minus x1, so that's going to be 0 minus 5 quantity squared. And the second parenthesis is the y's, and that's going to be 4 minus 4 quantity squared. So we have -5 quantity squared plus 0 quantity squared. That's 25. And I can say RS equals 5. Notice I do not have the segment bar above it because I'm not just naming it, I'm talking about its measurement. So RS equals 5. If you look at the original points, since they both have the same Y value, I know that this is a horizontal line, and I can just say, well, that's just like being on a number line. So 5 minus 0 is 5. So I could have used a shortcut in this one, but we want to make sure that we know how to use this formula. Okay, so let's do TU. And again, I'm just going to say x1, y1, x2, y2. TU equals big square root. We're going to subtract x2 minus x1, -1, minus -4 quantity squared. And for the y's, we have 1 minus -3 quantity squared. -1 minus -4 is a 3. 1 minus -3 is a 4. This is still all under the big square root. We have 9 plus 16, square root of 25. So TU equals 25. I'm sorry. TU equals 5. So we have a lot of good information here. We found the measurement of each of them. And now we were asked, are they congruent? So we're going to say, yes, RS is congruent to TU. If two segments have the same measurements, they do, they're both 5, then those segments are congruent. As soon as I'm talking about congruence, I have to put the segment bar above it because I'm saying that these two pictures are identical to each other. A segment has one measurement, length, but that's what congruent means. They are identical. Their measurements are 5. So we can say, yes, RS is congruent to TU, and we know that because RS, the measurement of RS, is equal to the measurement of TU. Okay. All right. So measuring segments on the number line and the coordinate plane.